Hey, so this is going to be the notes for the entirety of Chapter 16. We're just going to do one set of notes as we talk about electric charge and electric fields. The homework is broken into two sections, but this video should pretty well cover everything. And so as we jump into Chapter 16, we have to first understand this concept that when we talk about electric charge, we're talking about an electric charge that can be positive or negative and is a characteristic of every particle. They can be neutral, meaning we have zero charge, or we can have a negative charge or a positive charge. But down to our neutrons, protons, and electrons, we can say that certain things have a positive or a negative charge. And so that's the basic concept that we're going to work with here. As we talk about static electricity, typically what we're talking about is this idea of pulling electrons off of stuff and storing them on something else. So for instance, you rub a balloon against your head, the balloon is going to pick up electrons and build up a negative electric charge. And we can say for sure that negatives oppose each other. They don't want to gather together. Those like charges, they're going to repel. And so we can see in this image here on the right that two charged plastic rulers, if they're both negative or they're both positive, okay, they're going to repel each other. However, if we get a negatively charged particle or a negatively charged object with a positively charged object, they are going to attract each other. So we have that concept that that opposites attract. We mean that in terms of the electrical charge. The other thing that we need to understand is that this is conserved, meaning that we don't actually gain negative charge from the universe or take it away. It's not destroyed or created. It is just like energy, always there. It's a matter of how we arrange it. Are we going to pile up the negative charges that we have in one spot? Because then we gain the sense of negativity in the charge of an object. It's just really about how it's all organized or rearranged. Where do we put all the negative charge? Where do we put all the positive charge? And of course, we understand the concept that protons are positive and electrons are negative. And you can see this over here. If you look to the right, we can see this right there. You can see this water molecule, and you can see why we talk about it being a dipole. We have a negative nature in terms of the oxygen molecule, but because of the way that we're sharing the electrons. However, the hydrogen molecules, hydrogen atoms, come off as being positive. So on one side of a water molecule, you'll notice a positive nature, and the other you see a negative. So we see that behavior, which has a lot to do with how it's structured and how they're going to bind with other water molecules. Different materials conduct, some materials don't. Metals will move and balance charge. You can see that in our image here. If you have a lot of positive charge on one and it's neutral on the other, you're going to see that movement through a conductor in part B right here. But in part C, where wood's an insulator, you're not going to see that movement of electrical current. We did this experiment in class. We did a little bit of an electroscope. You can see this image here of our little gold leaves. We used aluminum leaves. They're all good, but when we push charge on this rod, it pushes down into the leaves and makes the leaves separate. So we can see sort of that happening with the electroscope. There's a few examples there. And then we get into the big daddy, Coulombs Law. And Coulombs Law is right here in the middle of the page, that F equals K Q1 Q2 over R squared. First, we need to understand K is a constant, 8.988 times 10 to the 9th. Now, in terms of its unit is essentially the same unit that it would take to cancel out the charge units and the radius units to create force. So I'm not going to worry too much about the unit other than say it's whatever cancels them all out. Tend not to worry about it. This is a constant that was basically derived in order to make the equation true. Like, what has to be there in order for it to work? Well, turns out this is our constant proportionality. Q1 and Q2, okay, these are charges, and all charges are measured in capital C, which stands for coulombs. Now, a coulomb is a big value, and so when we're talking about coulombs, typically we're talking about microcoulombs or nanocoulomb, something very small in terms of charge. If they're both positive, this force comes out positive. So a positive force means that the two objects are repelling each other. They're both negative, the force comes out positive. Only when the charges have opposing signs do you get a negative force. So a negative force means the objects are trying to pull towards each other. And the last thing you need to know is that r, we think of it as a radius, and that's the term we use, but it is the distance between, okay? And you can see that in this image right over here on the left. Literally, with Coulombs law, we're able to determine how much push and pull there are between two charged particles, and how hard or easy is it to move objects towards each other or away from each other. And down here we can see that unit, newtons times meter squared divided by coulomb squared. Again, it's a unit that's built to just cancel out the other units. One thing right here you're going to want to identify is that the charge of an electron or proton, we call it E, it's 1.602 times 10 to the negative 19. Now, if it is an electron, we know that's negative, which means we'd use a negative 1.602 times 10 to the negative 19th. If it's positive, because it's a proton, we use a positive. That's just the distinction, but that is our standard unit of, or we call it the elementary charge. As we keep coming down, we can do a lot of calculations with Coulombs law. One thing to keep in mind, Coulombs law is about forces, and you cannot add forces, because they're vectors, just by throwing them together. The only way you can add these forces is if they are in line with one another, which means, you know, if you have force 1 this way and force 2 that way, what you really need to do is break them into their x and y components. Okay? And then you can talk about the two x's adding together because they're both to the right, and here it's a subtraction. Okay, so maybe we end up with a big vector to the right and just a tiny vector up. To find the sum, you have to add up the vector components. Okay, this would be our fx, and this would be our fy, and you're probably going to have to use Pythagorean's theorem to find your total force. That's if they're not in direct line. But we've done this, it's just been a few months since we did any vector addition. But it is something that we still have to manage and still deal with. And that's going to kind of help you deal with some of these problems. Now, as we get into the second part of the content, we're going to start talking about electric fields, because even though there's a charge maybe isolated somewhere, the reality is that as you get closer to it, other charges are going to notice it from a distance. They're going to feel that push and pull. And because they feel that push and pull, we have to acknowledge that there's something being sent out, some influence being sent out. And we're going to call that an electric field. And the rules are that if you have a positively charged particle, the electric field will point outward in all directions. Okay? And if you have a negatively charged particle, the electric field will point inward from all directions. So you might ask yourself, okay, well, who determined which way these are pointing? Well, it's very simple. The electric field points the direction that positive charge flows. So ask yourself, if you brought another positive charge close by a positive charge, which way would it go? It would go away. It would want to go away. And so that electric field is going to point the direction a positive charge would flow. Over here, if I put a positive charge close to this negative charge, boy, it's going to come zinging in trying to get close to that negative charge. So electric fields always point the direction that a positive charge would flow. Okay? Either towards a negative or away from a positive. And we can calculate how strong that electric field is through this first equation. This is one of our two options. The electric field is the force felt on this guy here. We're going to call this Q. How much force does it feel divided by its charge? Now you've got to ask, okay, what unit are we going to use for electric fields? Well, if you think of a force as being in newtons, and charge, we just talked about, is measured in the capital C coulombs, the unit for electric field would be newtons per coulomb. Now remember, charge is usually really tiny. So will the force be. The force is going to be pretty small as well. But this idea, we take a small number divided by a small number. These electric field strengths are going to come out pretty reasonably sized, often in the thousands. So we're going to have these electric fields that tell us, how strong is the electric influence at a certain distance. Okay. Well, we got to recognize, hey, if I go further away from the charge, it's not going to be as strong. Electric field strength, you can think of it as the density of the electric field lines at a certain distance out. As you get out further, you can see the lines aren't as close together, which means we should be shrinking. But the problem is this formula doesn't give us anything to compare to radius or to distance. Well, if we replace the F in the equation with Coulombs Law, which we can do right down here, okay, we get some sort of cancellation. You can see how this Q is going to cancel one of the two Q's. All right, and we end up with E now equaling KQ over R squared. Now, this is important. The Q is no longer the little guy, all right? The big Q would be the big charge. We call that the point charge. Okay, it's the one that produces the field, not the one that we're going to bring close by. We call the test charge, okay, little q. So it's important we distinguish between whether we're talking about a test charge or the point charge. Okay, if it's the point charge, that's the one who causes the electric field. There's the test charge that we come in there and we push on it and we say, how hard is it to move it? That's the original equation version, where we just say, hey, how hard is it to move it? Here, we're not worrying about how hard it is to move. We want to know, hey, how big is that charge in the middle? We already know, so then we can determine how strong the electric field is. Still, we're going to measure that in newtons per coulomb. You'll see down here we have some variations of the formula. F equals QE. That's one that you commonly see. If you know the charge in the electric field, you should be able to find how much force is applied. Coincidentally, if you know the force, you also know, based on mass, the acceleration of a charged particle. If you can figure out what its mass is, then you'll know how much it's accelerating. Or if you know how much it accelerates, you can determine what the mass of the object is, or the charged particle is. We've got F equals ma Newton's laws, right? Electric fields can be added in much the same way that forces can. Here's a few examples of electric field lines being drawn. If you've ever drawn or seen iron filings above a magnet, it basically looks the same way. You'll notice that when you have two positive charges close together, you'll end up with a void right here in the middle where there's no real direction. You're kind of left in a neutral because both of them are pushing and pulling. And you'll see different things when you introduce negatives and positives. These field lines will continue to come through here. And so you'll see, hey, if you dropped a positive right there, boom, it's flying that way. It's being pushed from the right, pulled from the left. And one of the really cool things that we have learned to use these electric field lines for is actually parallel plates. We do a ton of stuff with this. What the parallel plates do for us is they take away a lot of the curvy nature of these electric field lines. It allows us to create very uniform, straight electric field lines, which means that if I were to send, say, an electron through here, okay, remember electrons would go towards the positive charge. If I send it really fast, I'm going to bend its path towards the positive. That's going to give me a really consistent way to direct and control the motion of these particles and aim them at something called a TV screen. And that's how TVs used to work when we used cathode ray tubes. We'll talk more about that when they come up a little bit later. See what else we got. Well, one of the famous physicists that worked with electricity and electric field lines and electric field strength was a man by the name of Faraday. And so we learned from Faraday, he designed something called the Faraday's Cage. Faraday's cage is basically you put a metal cage inside of an electric field. Those electric field lines don't pass through the middle of the Faraday cage. And the reason that happens is because it's actually easier for the electrons and protons to move around the outside of this metal cage. It's a conductor, so it naturally has the capacity to flow. As long as it's a closed system, it can go around and around and around faster than it could across. And so you could be in a lightning storm, you could be in a lot of different situations where you're seeing arcing, put yourself in that electric field, and yet you won't have electricity come inside of the cage. It's a way to protect and insulate things that are very sensitive to electrical fields. We can use them for computers and other things like that where we want to protect electronics. Then we have our last physicist and mathematician that we got to talk about in this unit, and it's Friedrich Gauss. Okay, Carl Friedrich Gauss. Very, very famous for a lot of different things, but one of them is his work with electric flux. Now, electric flux, you have to understand, is a measurement of how much electric field is going through an area of any surface. So he said, hey, I'm going to take a metal plate, slap it inside of an electric field. And depending on the orientation of that plate, he noticed different behaviors. And this is going to have a lot to do with something that happens later where we talk about induction and inducing a current. This has a lot to do with how we can generate electricity with magnetism. So there's a huge field we're going to get into a little bit later, but we have to have this basic understanding. When we talk about electric flux, we're talking about how much or what portion of the electric field goes through perpendicular to the surface. So this is a big, big deal. Here's our formula. This is a fun little symbol to write, by the way. I like to draw it like this. It's Greek letter phi, if you've ever heard phi something. It's the phi, or the flux, the electric flux, is equal to the electric field times the area of the shape times cosine of theta. Now here's the issue. Typically people want to think of theta in hey, look, from here to here, how much orientation have I created? The problem is we're not measuring parallel to the surface. We're measuring perpendicular to the surface. So in this formula, we have to start by finding what is perpendicular to the surface, and then ask how far is that from the electric field lines that are going this way. So there's perpendicular, there's the electric field line, that's how we determine the angle. And so for instance, let's say I had an electric field like this, and I laid a plate in that was parallel to the electric field. Well, what is the angle between perpendicular to the electric field and perpendicular to the surface and the electric field? Well, that would be an example of a 90-degree angle if you lay it flat inside that electric field. Well, the cosine of 90 is 0, and in this case, the electric flux would be 0. So it's important you understand we need it to be standing sort of upright, if you will, in order to have a parallel angle, right? So the angle between this and the electric field here, theta equals 0. And that would maximize our flux, okay? Now Gauss goes a little bit further. So there's our first formula, EA cosine of theta. He goes a little bit further and he says, hey, what if I took my electric field, right? I've got a charge. What if I put that electric field inside of a box? He said, all right, how would I figure out how much flux there's? So imagine there's a positive charge in there, right? And there's electric field coming out of all sides of my box. So that means there would technically be an electric flux coming through all sides of the box. Well, one thing that he was able to determine was that the total flux, okay, of the whole system was equal to the charge enclosed. Imagine that's a CL. The charge enclosed divided by, and there was this thing that kept coming up. It comes out as the permittivity of free space. It has this connection to it, and that epsilon naught, as we write it, has a value of 8.85 times 10 to the negative 12th. That's a value we actually see in a few different places throughout all of our calculations, but he found out that that constant of proportionality was division by epsilon naught. And you know, you can see a few applications to it, but the idea is that he was able to determine a lot about what charge would be inside of an object just by looking at how it's behaving and how it's affecting the outside world. And so that's a huge deal. This can go and get applied to so many different applications in medical and other fields, but we're going to stop there, and hopefully you have enough to get done. Good luck.